precautionary time is over, so let's get started on some calculus stuff. So now we get to finally do some calculus in section 1.4, 1.5, 1.6. We kind of do all these together. But anyway, so very similar topics. So let's just get started with section 1.4, and we're going to do looking at an introduction to limits. And limits are kind of the beginning of calculus here. So basically, let's just say what is the limit of a function. So really, I'm going to give you a visual first. If here's my f of x axis, and I have a graph, okay, and I don't even need to be defined at this point, but what they like to do is they like to call this specific x value, they like to call it x equals a. And of course, if it's defined up here at the height, you know, that would be f of a, but it is possible that I'm either not defined there or that f of a would be above this hole or things like that. But we're going to call this limit L. And so really what we want to do is we want to approach this from both sides. So I'll use red. So as my x values approach a from the right, you know, what does my graph approach? It approaches L, that height. So basically, what height do I approach? My graph is kind of sliding into that height of L, so I'm coming down that way. And when I approach from the left, I use green here. When I approach from the left, you know, what as x approaches a from the left, what height am I approaching? Well, I'm approaching a height of L again, and I'm actually doing that from the bottom side. I'm coming up from the bottom on that height. So as I approach from the right, as x approaches a from the right and from the left, my height actually approaches a height of L from both sides. So what we're going to say is we're going to say the limit as x approaches a from both sides exists and equals a height of L. So what is a limit? It's the height of a function as you approach a specific x value. So the limit of a function is a height. A height that the graph approaches. The limit of a function, so when I say u, I mean the graph or the sketch. So the limit of a function is the height it approaches as x approaches a specific value. And if it's not specified, you can approach that value, which in this case is x equals a, from both sides. Okay, so hopefully the concept of a limit makes sense, and then we're going to dive into the details of it, which is a little more involved. Okay, so let's just look at an example. If I've got f of x equals x cubed, okay, we know what that looks like. It's a swerve that goes through the origin, and let's let a equal 2. Okay, well, we know this is continuous functions defined everywhere, but if I plug in 2, I actually get a height of 8. So that would be the limit that I approach. So once again, if I'm approaching from the right, I'll use red from the right. What's my graph doing? It's coming down on a height of 8, right? And then if I approach 2 from the left, is green. Usually I use blue from the left, but anyway, then I'm approaching that height of 8 from below. So anyway, both of them from the right or from the left, as I get closer and closer to 2, then I'm getting closer and closer to a height of 8. And of course, in this case, this actually equals f of 2, right? So in this case, it's okay to plug in. But we can't always plug in. So polynomials is pretty easy. It's just you plug it in, and that's going to be the limit. And so the way I would show this is that the limit as x approaches 2 from both sides of f of x exists and equals L. So what's f of x? So of x cubed exists and equals 8. Okay, so that's how we write it in shorthand. The limit as x approaches 2, once again from both sides, if I didn't specify, of x cubed equals 8. Okay, so hopefully that makes sense. And then now I'm going to draw it out a little bit detail. I'm going to go back to black. So anyway, let's look at just an easy example. I'm gonna use a little bit different one than I have in my notes, because you can always look in my notes as well. But let's just look at f of x equals, let's just say 2x plus 3. Okay, so if I have f of x equals 2x plus 3, we know what that graph looks like, right? And I'm gonna let a equal 1, that specific x value. And then what we want to do is find out what's L equal. Well, in this case, if we look at the graph, okay, we have, if you plug in 0, we get 3, right? If we plug in 1, you get 5. So anyway, 1, you get 5. And if I plug in 2, I'm going to get, what do we get? 7. So anyway, it's a line with a slope of 2, right? And then what I'm doing here is a equals 1. Well, it's pretty obvious on the graph that I'm approaching. So let's approach 1 from the right. Okay, then what am I getting? And what we could do is, to get a visual here, if I have, you know, x and then f of x, and once again I'm approaching from the right here. Well, let's do that. If I come in from the right, let's just start at 2. If I plug in 2, I'm getting a height of 7, right? So 2 times 2 plus 3, that's 7. Well, let's get a lot closer to 1. So let's go 1.1. What if I plug in 1.1? Well, if I double it, I get 2.2, and then add 3, I get 5.2, right? So that's getting closer to a height of 5 here from the top side. So let's get closer to 1. 1.01, if I plug that in, I get 2.02 plus 3 is 5.02. And let's get even closer. I'm going to plug in 1 and 1/1000th, so 1.001. Double that is 2 2/2000 plus 3 is 5 2/2000, so 5.002. And what we notice here is, what am I approaching on for the x values? I'm approaching 1 from the right. So I can put a little plus sign up there saying I approach 1 from the right there. And then what's my height? What height am I approaching? Well, as you can see, this is going to get closer and closer to 5 from the top side. So 5 from above, I can put a little plus sign there. So 1 for the x's means to the right. I mean, not 1. The plus sign for the x's means from the right. Plus sign for the y's or the f of x's means from above. And of course, if I'm from the left on the x's, I could put a little minus sign there, which I'll do. And if I'm coming from below, I'll put a little minus sign. So I am approaching that height of 5 when I approach from the right-hand side. Now, what you're going to notice in section 1.6 is this is going to be the right-handed limit. So the right-handed limit is actually going to be 5. So I'll just note that the right-handed limit exists and equals 5. Okay, so now let's approach from the left. So I like using blue from the left. So as I approach 1 from the left, so, and once again, we try and stay away from plotting points and figuring out what's going on. This is a graph that we can see what's going on very easily. It's going to be easy to see that I'm going to approach that height of 5 as I approach 1 from the left. So let's go ahead and do it. If I started with 0, what do you get? I get a height of 3. Well, that doesn't really help us much. Let's get closer to 1. So what about 0.9? If I double that, I get 1.8. And then plus 3 is 4.8, right? And let's get even closer. So 0.99. if I double that, what do I get? 1.98 plus 3 is 4.98. Okay, and let's get even closer. What if I get 0.999? Now the math's getting a little hard. If I double that, well, you're doubling all but 1/1000th, which is 2 1,000ths that you don't get. So instead of getting 2, I'm going to get 1.998 plus 3 is 4.998. And you can see the pattern here. If I went 0.9999 and then added 3, I'm going to get 4.9998. So we're just inserting more 9s here if I have more 9s on the left side. But the reality is, what are these, what's this approaching? Instead of going straight down, I kind of ran out of room here. But this is approaching 1. X is approaching 1 from below, from the left. So I put a little minus sign. So that's what I'm doing. That's what I'm doing here. And what's my heights approaching? I'm approaching a height of 5, but I'm approaching it from the bottom side, right? So I am approaching a height of 5, but I'm approaching it from below or from underneath, okay? So this is going to be the left-handed limit. So as I approach 1 from the left, I'm approaching a height of 5. So the left-handed limit also exists and equals 5. But since they both exist and are equal, then we're going to go back and say, okay, the limit of this function exists and equals 5. Okay, so that's what L is. The limit exists and equals 5. So hopefully that makes sense. This is pretty easy. Obviously, we can plug in here because if you just plugged in 1, 2 times 1 plus 3 gives you a height of 5, but that doesn't always work. So we don't always have nice functions there. So we got to be a little bit careful on that. All right, so let's look at some other examples. And so it is important. We don't. So limit of a function. So let me just kind of draw that out as a definition. The limit of f of x, once again, that's the height you approach. The limit of f of x as x approaches a and once again, that's the height you approach. How are we getting, it's not a definition, let's just look at notation, I guess. We're going to write this, the limit as x approaches a of f of x, if it exists, it equals capital L. So that's the notation, not a definition. It's more notation here on how we're going to write that. So what could we say? We could say for that previous example, the limit as x approaches 1 of 2x plus 3 exists and equals 5. Okay, so that's previous example. There is how we would write that. And once again, for polynomials, it's pretty easy. We're going to find out, we're going to have a theorem that says, hey, we can just plug in and get that. Okay, so the question is, you know, how do we define that? But before we do that, I want to do a different example where it's not so obvious. So example here, let's look at we want to find the limit as x approaches 2 of x squared minus 4 over x minus 2. Okay, so is there a specific height that we approach here? Well, once again, I don't want to sit here and plug in a bunch of numbers, but if I plugged in 2, so if this is f of x, what's f of 2? If I plug in 2, I'm going to get 0 over 0, which is indeterminate, right? So I don't have an answer there. So I could get close to 2 on the bottom, 1.9, 1.99. I could get close to 2 on the top, 2.1, 2.01, etc. See what those are. But the reality is we can use some algebraic manipulation to see what this looks like. So if we have the graph and we can see what it looks like, that's always a good deal. So we can factor that as x plus 2 times x minus 2 on top, because it's a difference of 2 perfect squares. or difference of two squares, all over x minus 2. And then what we can do here is we can actually cancel out the x minus 2's, because the limit as x approaches 2, I'm approaching 2, but I never really specifically touch it. So I didn't really say that before, but for a limit of a function, you can get as close as you want to a, but we're not actually touching that point. So when I plug it in here, we really can't do that. Of course, here it's not defined, but when we were doing it before, we could do it, but that's not really what a limit is. Limit of a function is only as you approach it, not when you actually hit that point. And I'm going to give you an example of why that's the case. So anyway, this is equivalent to x plus 2. And where is it equivalent to that? On the domain of f. So this is back to what we did in section 1, right? And so what could I do now? I could just plug in what this is. If I plug in 2 here, I get a height of 4. So what happens is it's equivalent to x plus 2, except when x equals 2, and I would have a height of 4 that I don't hit. And of course, 0, 2 would be on your graph. This is just a line graph with a hole at 2, 4. But once again, so that's what this graph is actually here. F of x equals this. And the domain of f is all reals excluding 2. And the range of f, the heights I hit, is the set of all reals excluding 4. So we did stuff like this before. This is why we did it. But basically, as I approach 2 from above or below, I'm gonna approach a height of 4 here. So what I can say is that the limit as x approaches 2 of x squared minus 4 over x plus 2, no, x minus 2 exists and equals the height of 4, okay, because it's equivalent to x plus 2 on its domain, okay, which the domain all reals except for 2, okay. But anyway, if I plugged in 2 there, I could actually do it and I get a height of 4. All right. So one more quick example of why you can't just plug in. What if I had a split function? So example, if I have f of x as a split function and it equals x squared minus 4 over x minus 2, if x is not equal to 2, and it's going to equal 5 if x does equal 2. Well, if I'm going to graph this thing, the graph is just like what we had before, except I have, I have a hole there at over 2 up 4. And of course, I got a y-intercept of 2 here. But anyway, what I'm going to do here is now I've got f of x equals 5 if x equals 2. So I actually have a height here of 5. So now what is the domain of f? So the domain of f in this case is all real numbers, because for the top one, you can plug in anything except 2 would be fine. And then if x does equal 2, we're defined now. And of course, what is the range if you wanted to say, hey, what's the range of this f? Well, I still don't hit a height of 4, so it's all reals excluding a height of 4. Okay, or for those of you that love intervals, negative infinity to 4, not including 4 to not including 4 to infinity. Okay, but anyway, so in this case, what is the question would be, what is the limit as x approaches 2 of f of x? Well, and of course f of x is this split function here, it's this whole thing. But as I approach 2, I'm not touching it, so I'm not really worried about that. It just becomes this. As I approach 2 from both sides, once again, I'll use red from the right and blue from the left. What height am I approaching? I'm approaching 4 from the right, and as I approach 2 from the left, I'm also approaching a height of 4. So we can say here also that the limit as x approaches 2 of this f of x exists and equals 4. Notice that is not plugging in 2. So if I plugged in 2, I'm going to get 5. So this does not equal, this is not equal to f of 2 in this case. Okay, so some specific examples here to kind of give you a concept of what a limit is. So can you give me a thumbs up if you kind of follow what I'm talking about with a limit? I know you know how to use the chat. Come on, Hawk fans, where are you? All right, we got one. So I assume that one person's still conscious and paying attention to this stuff. So that's good. All right, we got a couple people. All right. And once again, if you have questions along the way, feel free to just hit your voice thing and let me know, or type in a chat, because I think I see it when you type it in there. All right. All right. So now what we're going to do is we're going to get a little more specific on the what it means to be a limit. Okay. And so we're going to get a formal definition, which is really what you're going to want to know here. So we need this is a quiz you don't want to have, so I guess you better be rooting for the Hawks, I guess, but probably won't be on this. It'll probably be on section 1.1 through 1.3, just to be nice to you. So formal definition. All right, formal definition is this of a limit. So first of all, to even talk about a limit, we have to have a function, and we got to be defined around it. So we're going to say let f be defined. So if I say just f, the book always says let f of x be a function. Well, duh. I'm not going to use f of x or g of x or h of x if it's not a function. So that's redundant in my world. So I'm going to say let f be a function. No, I'm not going to say that. What am I doing? I don't want to say that. The book always says that. That's redundant to me. So I don't want to be redundant. So instead of saying let f be a function, we already know it's a function. So I'm going to go back and I'm going to say let f be defined. So we already know it's a function. Defined on some open interval containing a except possibly a itself. So x equals a is the specific value. So if that's some open interval containing a except at possibly a itself. Now, what do you know about me and writing stuff out? And you gotta be careful how you read this, because this isn't English. This is this a containing a. It's really x equals a, right? So let's just look at a picture of that. So here's a, okay. I got to be defined on some open interval around a except possibly at a. So I got to be defined to the right, and I got to be defined to the left, and there's infinitely many places where I got to be defined. So I got to have that for my function. I don't care if I'm defined at x equals a. I don't care about that, right? Okay. So I don't like writing all this. This is hard for me. So I'm gonna just give you what I do for that formal definition. So formal definition, here we go. This is how I write it. Let f, which we already know is a function, let f be defined on I, which is some open interval containing a. So I is I for interval, some open interval containing a, or I minus the set containing point A, x equals a. So anyway, this is that same picture. So I'm either defined all the way through on both sides of the point, including the point, or not including the point, x equals a. Doesn't really matter for limits, because we can get as close as we want to x equals a without touching it. Okay, so then, so we have that. Then the limit as x approaches a exists and equals L, which I'm going to write like this. The limit as x approaches a of f of x exists and equals L, if and only if. So once again, it's a definition. Definitions go both ways. So that's if and only if. Now we're going to get into the calculus part of this. For all epsilons greater than 0, sorry, there's a little smudge there. I don't know where that came from. For all epsilons greater than 0, so what's epsilon? Epsilon is a tiny number. So for any tiny epsilon number, positive number, there exists, oh, wait a minute, you guys don't know this notation yet. Sorry, let me erase. If and only if, for all, I gotta go back and draw. For all tiny numbers, epsilons greater than 0, there exists a delta greater than 0, so that's another number, positive number, such that what happens? 0, if 0 is less than the absolute value of x minus a is less than that delta, so I'm going to say such that if 0 is less than x minus a is less than delta, then the absolute value of f of x minus L is going to be less than that epsilon. All right, so this is the fun part of the day. This is why you're glad you showed up today on an early Friday morning. That's going to be the limit. So we need a picture. So the question is, what is this epsilon? This epsilon is around f of x. So it's a window. It's a window around your limit. What the heck? This keeps changing on me. It's a window about, what's it doing? It's a window about L. And then, I don't know, something's happening here. And then this is a window about your, come on, draw. This is a window about your, about x equals a. So I'm going to erase this because it's messing up on me. All right. So let's draw our picture. Okay, here's A. I'm defined around on some open interval containing A except possibly A itself. We know that this is L. Okay, and then what do we say? The limit, and we're looking at the limit as x approaches A from both sides of f of x. Where's f of x? This is my f of x. This drawing here, right? This exists and equals L. If and only if, for any epsilon, so for any tiny number, tiny positive number, what did we say? It said that, for that part, it said the absolute value of f of x minus L is going to be less than epsilon. Well, that means that I have a window around my limit. Okay, so if I plug in something, it's going to fit it around A. So this is L plus epsilon. This is L minus epsilon. Okay, so I'll give an example. If my limit was 4, like it was on a previous example, and my epsilon is 1, then this would be 4 plus 1 on the top side, which would be 5, and it'd be 4 minus 1 on the bottom side, which is 3. So I'd have a vertical window from 3 to 5 containing 4 in the middle. And so that's really all this does, is this is an epsilon window around L. Okay? But I said for any epsilon, you're going to be able to find a delta. So what we're going to do is we're going to reverse map this down here. So we're going to reverse map this window. And then basically what I want to do is I want to find a delta for any given epsilon, no matter how tiny, no matter how close to L on both sides, for the L plus epsilon, L minus epsilon, I'm going to be able to find a delta. So there exists a delta. So this would be, now that delta is a window, it's a tiny number. It could be, well, it could be a big number, but it's a number. Whoops, sorry, that's a minus. A minus delta to A plus delta. So when we have 0 is less than the absolute value of x minus a, that just means x can't equal a, right? So since this absolute value is always greater than or equal to 0, but this says right here that x does not equal a. So it's only a positive number. And then less than delta. So this is my delta window around a. So basically, if you give me any tiny epsilon around L, tiny epsilon window around L, this limit is going to exist and equal L if and only if for any epsilon that you give me here, I can find a delta that guarantees, now here's where, let's go back in here, that any value here, so this, let's just call that x1, is going to get mapped, so that's f of x1, right? It's going to get mapped, here's x2. Any x inside this window, so once again, this is a delta window, any x's in here are going to get mapped into this epsilon window. So here's f of x plus 2, or excuse me, f of x2. So the second one. So basically, no matter what ones I pick in here, no matter what x's, they're all going to map into that epsilon window. So if I can do this for any epsilon that you give me, any tiny window around L, if I can find a delta that guarantees that all the x's get mapped inside that, so this is almost like a vacuum, right? Like it gets sucked up in there and it stays inside the vacuum, this window up here. If I can find that, then the limit exists and equals L. So that's the definition. So now the question is, how do you do that in practice? And I'm going to make you do it for lines after I show you how. Don't worry, there's still instruction to come. You don't have to figure this out on your own. But notice if you're reading your notes or my notes from class, this is going to be a little bit difficult task. I'm going to guarantee, or I'm not guarantee, but I'm pretty confident that anybody that had already taken calculus has not done this. So I promised you that I was going to give you stuff that you didn't do, a little more theory. But anyway, so I do have prettier pictures of this, but let's look at an example. So we're going to use the definition, the formal definition, to prove that the limit as x approaches, let's do x approaches 2 of x plus 3 exists and equals, what would that equal? Anybody want to chime in on the chat? What would this equal? You able to figure that out? Yeah, 5, absolutely. So we could actually just plug that in. That's just a line. Everything's nice, right? Well, first of all, I gotta use the formal definition. So the definition says let f be defined on some open interval containing x equals 2, except possibly at 2. Well, is it? What's the domain of f? The domain of f is all real numbers. So I'm defined. You do need to note that because we got to make sure that we can use that definition. So I'm defined on some open interval. The real number line is an open interval from minus infinity to plus infinity. I don't care if I'm defined at 2, but I am for this function f of x right here. Okay, so once again, this is a, 2 is a, f of x equals x plus 3, and then 5 is my L, right? So if you're not sure, just got to get used to writing this out. The limit as x approaches a of f of x exists and equals L. So anyway, that's what those values are for this one. So we've got that. And then to prove it, we need to do a little scratch work. So it says for any epsilon greater than 0, we can find a delta. So let's pick an epsilon. But what we're going to do is let I'm trying to think. This isn't 1.4. I'm getting into 1.5 here. Well, let's do it in general. So let epsilon be greater than 0. Okay. So this is any specific tiny number, and what we need to do is find a delta greater than 0. So for any epsilon greater than 0, there exists a delta. So we need to find a delta greater than 0 such that what? And then we're going to write out what we have. 0 is less than the absolute value of x minus a. What's a? A is 2, is less than delta, would imply or guarantee. So if this, then that, we could just use an arrow. So this implies that the absolute value of f of x, which is x plus 3, minus L, so minus 5, is less than epsilon, right? So that's what we need. So this is, notice what I put. From the definition, I said that, 0 is less than the absolute value of x minus a is less than delta, and this was the absolute value of f of x minus L is less than epsilon, right? So what I'm going to do is I'm going to work with the finish line. Here's the finish line that I want, and then I'm going to come back and find my delta. So if I do this and I simplify this, I end up with the absolute value of x minus 2 is less than epsilon, right? If I combine that, well, what do I have here? I have x minus 2 is less than delta needs to guarantee this. So in this case, because I have the absolute value of x minus 2 on both of them, I can just say set epsilon equal to delta. Okay, so basically I found it pretty simply on this one. So now let's go back and let me do it. So that was my scratch work. Okay, that was my scratch work. So now I'm going to prove it. Proof. So the limit as x approaches 2 of x plus 3 exists and equals 5. So first of all, the domain of f is all real numbers. So we got that. So we're defined. And then now we're going to let set. This is what we're going to do. Let set. So that's my key here. So proof. Let epsilon be greater than 0. Set delta equal to epsilon. Then 0 is less than the absolute value of x minus a. What's a? A was 2. Is less than delta. What does that imply? Well, we need it to end up implying that absolute value of f of x, x plus 3 minus 5 is less than epsilon. That's what we need, right? So what we're going to do is we're going to work backwards from our previous stuff. Okay, I know this is awkward initially, but we see it enough. This is going to get better, I promise you. Okay, so we're going to work backwards here. Backwards out from our scratch work. On scratch work. How do you spell scratch? T-C-H. All right. So anyway, what I'm going to do here then is I'm going to work with the right side. So this implies the absolute value of x minus 2 is less than delta. Okay, but what did I set delta equal to? Epsilon, right? So this is less than epsilon, right? I just plugged in epsilon for delta, which implies what? Then I could rewrite it as, just going back up. So x plus 3 minus 5 is less than epsilon, which is what I wanted. That was what I wanted there. So anyway, this proves it. So for any epsilon we had, any epsilon window around the limit of 5 for this function, I could find a delta. And in this case, it's just delta equals epsilon. Okay, so that's kind of the process. I'm going to do a couple more, but I'm going to do a section 1.4 example of this, hopefully. show the limit holds, excuse me, let me do section 1.4. Find delta for epsilon equals 0.1 for the limit, same one. Limit as x approaches 2 of x plus 3. Okay, so we need to find a delta for epsilon equals 0.1. Well, you already did it in general, so you know the delta is going to equal 0.1, right? But I want to show you a picture of this so that we kind of see what's going on. So when we plug in 0, we get 3. When we plug in 1, we get 4. When we plug in 2, we get 5, right? Now, once again, I don't care if I'm defined there, but this is my graph, right? It's just a line with a slope of 1. So 5 is my L, 2 is my A, right? So basically, if I've got epsilon equals 0.1, so I'm gonna change colors here. So let's see. We use I was using blue there, but I'm using blue for my graph. So if epsilon is my window, so that's my epsilon window. What would my epsilon window be? It'd be 0.1 above 5 and 0.1 below 5. So it would be from 4.9 to 5.1. So basically what I need to do is I need to find a delta window around 2 where every x value is going to map up inside of there. Okay, so in this case, let's drop it back and say, okay, and you're going to find out that we like to find the biggest window too. So basically, what would that window be? Well, in this case, that window of 0.1, so if delta equals 0.1, then that would be anything from 1.9 to 2.1. Any x values in there would map up. So if I had 1.95, it's going to map up in that window. If I had 2.03, it's going to map up between 4.9 and 5.1. And so this is kind of what it looks like for a specific number, not just a general epsilon and delta for any value. But anyway, I wanted to give you a specific one. But the question is still, Tim, how do you know, right? I think that would be your question. How do you know that for this epsilon that the delta is okay to be the same? By the way, any smaller delta would work. If I wanted to pick delta equals 0.0001, that would be a smaller window around L here, or not L, around A, but it would still, all of those would still map into this epsilon window. So I could be smaller than the delta that I picked. I could be smaller than that. But what my process is going to do for lines is it's going to give you the biggest such window that we can have. So I want, really, when I am having you do this, I want the biggest delta window that we can have that still guarantees that mapping through the tunnel. Okay. So let's go back. How did we do it? Well, first of all, let me clear this off. Need a little room. We're going to do the scratch work again, right? So we're gonna say, so here's our scratch work. Let epsilon equals 0.1, and we need to find a delta greater than 0 such that what? 0 is less than the absolute value of x minus a, which is 2 is less than delta, implies or guarantees that the absolute value of f of x, which was x plus 3, minus L, which is 5, is less than epsilon, but I know epsilon, so it's less than 0.1. So I'm going to rewrite this down here. 0 is less than the absolute value of x minus 2 is less than delta. I need to find that delta. Would imply or guarantee that the absolute value of f of x minus L, which is 5, is less than 0.1, because that was given. All right. Get rid of that. Running out of room. Need a bigger board. Okay. Anyway, coming back here. So what I'm going to do is I'm going to work with the finish line. I'm going to work with the finish line. All right. So I'm going to work with this. And then, so this implies that absolute value of x minus 2 is less than 0.1. And notice that I had x minus 2 is less, absolute value of x minus 2 is less than delta. So I'm going to set this equal to my delta. So that one was pretty easy. I've got a few minutes left here. So I let you out early last time. It might take me more than 3 minutes to do this, but I want to give you one where it's not just the same. So let's go back to the original one. The original one was, so we want to prove, using the definition, that the limit as x approaches 1, I think it was, of 2x plus 3. I believe we did this and showed that that was going to be 5 by graphical methods, because we could just plug it in, right? So I think that's the one we do, or did. So first of all, I need to note that the domain of f is all real numbers, so I'm certainly defined on some open interval containing x equals 1, except possibly 1 itself, but I'm actually defined at 1 as well. So I've got that, and then I need to do my scratch work. All right, I'm going to try and do this on the left. So, so I need to let epsilon be greater than 0. There's my warning bell. Let epsilon be greater than 0, so I'll finish this up. I need to find a delta greater than 0 such that what? 0 is less than or equal to the absolute value of x minus a, which is 1, is less than delta, would imply or guarantee that the absolute value of f of x, which is 2x plus 3 minus 5, is less than epsilon. Okay, so what did I say I'm going to do? I'm going to work with the finish line here. This is my finish line, and then try and get it in terms of the absolute value of x minus 1, so that I could, for that given epsilon, I need to find this delta. So keep working here. Basically, I can do algebraic simplification here. So this is the absolute value of 2x minus 2 is less than epsilon, right? So what can I do here? I can factor out a 2. So it's the absolute value of 2 times the quantity x minus 1 would be less than epsilon. And then what's that guarantee? 2 times the absolute value. So the absolute value of a times b is the absolute value of a times the absolute value of b. So I've got 2, and the absolute value of 2 is 2, right? So it's 2 times the absolute value of x minus 1 is less than epsilon, which, what does that imply? That implies the absolute value of x minus 1 is less than epsilon over 2. So I can just divide both sides. I can just divide both sides by 2, right? So anyway, so this is my scratch work. So then what I want to do, so now, what did I have over here? Absolute value of x minus 1 is less than delta. I'm trying to find the delta. So I need to set delta equal to epsilon over 2. So I let epsilon be greater than 0. I'm going to set delta equal to epsilon over 2, and then I'm going to work this backwards, and should be good to go. So I'm going to finish up with a proof, or how I do that. So now on the proof, it's let set, remember, let set. So I'm going to let epsilon be greater than 0, set delta equal to epsilon over 2, and then I'm going to work backwards. Then 0 is less than the absolute value of x minus 1 is less than delta, implies what? Now I'm going to take the right part of this. I'm going to take the right part of that. And so that's going to imply that the absolute value of absolute value of x minus 1. So I'm just taking the right part of the inequality. But instead of delta, we've got epsilon over 2. So I can plug that in there. So this is less than epsilon over 2. And then what I'm doing is I'm working backwards on my scratch work. So I'm just undoing the steps that I did on the scratch works, and I'm going to multiply both sides by 2. And if you multiply both sides by a positive number, the inequality stays the same. And then I could put that absolute value of 2 inside. And then what does that imply? That implies the absolute value of 2x minus 2 is less than epsilon, which implies the absolute value of what did we want? F of x, which is 2x plus 3, and then minus 5 is less than epsilon. And so I've got what I want. Absolute value of f of x minus L is less than epsilon. And so to finish it up, I can say, therefore, the limit as x approaches 1 of 2x plus 3 exists and equals 5. All right, and we're done. So you'll have to do this by sometime next week, but read 1.4, which is specific values of epsilon, and 1.5, and we're good. All right, have a great weekend. Thanks.